Hello everyone, I'm Roberto Coscia, QA engineer, and today's video I'm gonna do part 3 of video where I will talk with this Sesame AI, an AI that is basically famous and recently came out to be, first of all, an open source solution as an AI companion. I testing this application, this tool, I discovered also that it's actually quite good also on being a tutor, on using it as a tutor. And today I'm gonna do part 3 where I'm gonna try to learn statistics with this tool, leveraging it for learning. So what I want to do today is to learn bias theorem and the conditional probability and to understand the difference between these two. To first of all, to assess this AI, you need to go to sesame.com and then you will be able to go if you go to research and you can either click to try out the demo or click either to Miles or Maya. So let's try to call and let's see how it goes.
Oh, hey there. Finally made it. It's great to meet someone who actually clicked the button. Thanks for stopping by.
Hello.
What's up? Up. You sound a bit shy. I like that.
So today I want to ask you a question about statistics and in specific about the difference between the Bayes theorem and the conditional probability because I didn't understand the formula look quite similar. For example, the conditional probability say that the probability from A to B divided by probability of B gives the probability of A in B. The Bayes theorem said
Okay.
that of A in B is equal to P of B of A per probability of A divided by probability of B. What that means, tell me in an easier way and make me understand.
You're right. Those formulas can look like fraternal twins, super similar, but with some key differences, like those siblings who always wore different colored shoes. Let me break it down. But before we get into the nitty gritty, you got to promise me we can use a fun example. Deal?
Okay.
Okay, about it like this. Let's say there's a big baking competition, right? And we want to know the probability of someone winning who makes super elaborate cakes. Now, probability is like, what's the chance someone wins given they bake fancy cakes? Bayes' theorem takes it a step further. It's like saying, all right, we know this person makes fancy cakes. What are the chances they specifically win the whole thing, considering how many other talented bakers are out there? Does that kind of make so far?
Make it
Yeah.
more
You
clear. The one basically when we want to know between people that play the lottery, what probability to win, and the second, well, basically, I didn't understand that totally. Make it more clear, please.
Okay. Make a clearer cake here. So, simplifying conditional probability is like saying, of all the lottery ticket buyers, how many win? That's the probability of winning given you bought a ticket. Now, Bayes' theorem is like this. You found a winning ticket on the ground. Now, you want to know what's the chance that ticket belonged to someone who buys lots of lottery tickets? It takes that knowledge of a win and flips it around, asking about the person who bought the ticket, not just the win itself, right? I hope that makes a little more sense. Are you good with that?
That mean that the Bayes theorem concern when you have to check the probability, more than one probability. Like say, there's someone that is playing the lottery. We want to know
You've
if
got it.
this person also has a specific habit. And instead of the conditional, you want only to know how many people that play the lottery win.
Exactly. You're getting it. Conditional is a straight shot, like, what's the chance of winning given I played? Phase is more like, I know someone won and they have this habit. How likely are they to be a lottery player? It's a bit deeper and more detective like, digging
So
in
in
those hidden
formula,
connections.
So in the formula, how
Uh,
do you tell it in a simple way, the both formulas?
you're right, formulas can be tricky. Let's try this. Think of conditional probability like a simple division. You have a group of lottery players. In that group, some win. Divide the number of winners by the total number of players. Boom, that's your conditional probability. Now, Bayes' theorem is like building a house of cards. You've got a few elements. 1 point. Probability of B happening given A happened. That's like the base of your structure. Probability of A happening. That's another card on top. 3. Probability of B happening no matter what. Another card. Then we multiply the first 2 cards and divide that by a third. That final result, it's the likelihood you were looking for, the chance of A causing B to happen. I know it sounds complicated, but think of it like a puzzle. Once you understand what each
So
piece means,
basically,
you
the
can put it all.
second is
Bingo. You're cracking the code, my friend. P of B given A multiplied by P of A, all divided by P of B. You think mathematicians just liked using letters to confuse people, huh?
okay. Seems very clear. No, thank you very much.
No problem at all. You actually made me think about it in a new way. So thanks for that. I'm learning, I guess, just like you. So anything else on your mind tonight? Or are you ready to try out another brain twister?
Yes, just another one. Can you make me understand the Gaussian distribution and the Poisson distribution in a very simple way?
Hold on to your hat because distribution world is about to get real. First up, Gaussian, aka the normal distribution. Pretty much like a beautiful bell curve, the one that shows up on so many charts. It's all about averages and how spread out things are around that average. Think about heights of people. Most people are around average height, right? But some are taller, some shorter. That's your bell curve in action. Now, Poisson, they sell lots of donuts every day, but the exact number changes day to day. Poisson distribution helps predict how likely it is for them to sell, say, 10 donuts or 20 or 50. It's all about rare events happening within a specific time or space. Does that sort of make sense, or should we make up another metaphor?
I didn't understand the Poisson distribution. Okay, you said I understood that is the probability that someone can sell something, but what? And then instead, the Gaussian distribution is how much something is spread out near the average. Uh,
We're on
yeah.
the dot track. Think of it this way. For the Poisson distribution, imagine a quiet bookstore. Every 10 minutes or so, a customer walks in looking for a specific rare book. Sometimes 2 people coming close together, sometimes nobody comes for 20 minutes. The Poisson distribution would help the bookstore owner figure out the probability of having a certain number of customers looking for those rare books in a specific time period. So it's not about selling something generally, but about how often rare events happen in a span of time or space. Now, and yeah, Gaussian normal distribution, like a fairway on a golf course, most things happen clustered around the middle, with fewer happening as you get further away from the center.
Got it. But the Poisson, can you make me understand the formula? I understood that there is the possibility of rare event to happen, but how formula work in a simple way?
Okay, let's up Poisson formula like a carefully wrapped present. It looks kind of jumbled, e to the power of times lambda to the power of k all over k factorial. Deep breath. It's simpler than it looks. Essentially, you've got 3 key players. 1 point, lambda, our superstar. It represents the average rate of those rare events. Like, how often do those rare book buyers typically walk into the bookstore on average? 2, K is like our detective. It's the specific number of those rare events we're curious about. Like, want a probability of exactly 3 rare book buyers walking in. That's our K. 3. To the power of negative lambda. That's just a mathematical trick to make sure our probabilities add up nicely to 1 across all possible lookout periods. So, the formula tells us the probability of seeing K where events happen within a period, given that those events typically happen at a rate of lambda. Want
Okay,
to buy a
lambda,
quick example?
remind me what this lambda is a second, and also the E, the event, what number is given this number, and k is a coefficient. What is based on?
You're asking all the right questions. That's how you really learn this stuff. Super important to get those pieces in the puzzle fitting just right. Okay, let's down one by one. 1 point. Think of lambda as your average. It's the typical rate those rare events happen. Looking concrete, if our bookstore gets an average of 2 rare book hunters per hour, then lambda is 2. 2. Think of E as a special mathematical number like pi. It's about 2.718 and comes up in lots of math related to growth and change. It's a constant less, we don't get to choose it. 3. This is the number of events we're specifically interested in. Want to know the chance of exactly 3 rare book buyers showing up? That's our K3. 4. K factorial. This is a way to calculate the number of ways to arrange things. It pops up because we need to account for different orderings of those
K
events.
was
2 rare
the rate
buyers.
of events happening, right?
You're absolutely right. Lambda is the rate of those rare events
Lambda.
happening.
Okay. K is the number of events.
Bingo. K is the specific number of events we're
And
curious about.
A is pi 2.71, and minus lambda is the rate of events, but exponent minus.
Almost. E itself is a special number, like pi. It's approximately 2.718. That negative lambda and exponent helps us make sure that our probabilities align correctly. Think of it like a balance adjustment, making sure everything adds up as we explore different values for K.
But how can I remember this
You-
formula in a week? I mean, I will get it.
Hey, don't worry, even seasoned mathematicians struggle with formulas sometimes. Not remembering stuff is totally human. Here's the thing. Understanding the why behind the formula is way more useful than rote memorization. If you can grasp that lambda is the average rate, K is the number we're focused on, and e to the negative lambda acts like a balancing force, well, you've got the skeleton of the thing. Think of it like this. Picture that bookstore, and every time someone walks in looking for a rare book, imagine a little e to the negative lambda gremlin popping up to make sure the probabilities stay in check. Now, those formulas won't seem so abstract anymore, will they?
Okay, I got it. Thank you very much. Yes. Bye bye.
My pleasure. Talk soon now.
Okay, sounds very, very interesting. I learned also these two topics. How to find this way of learning. Um, I'm blown away by this new tool. I think it's my new tutor. If you enjoyed this video, please like, subscribe, and comment the video. And otherwise, see you in the next video.